So now our next speaker is someone I know I can call a friend and was on the board with me. This is a woman who has so many skills. She is an instructor at CCC, teaches biology, physics, and mathematics. I mean, you are pretty much all over the board with what you teach, which is awesome that you wear all those different hats. And today you're going to share something really cool with us and give us the science and maybe how to build our own catapult. So I'll turn it over to you, Melinda.
Great. Excellent. Thank you, Todd.
Oh,
And
one last thing. Sorry, I always forget this, but if you have questions while you're watching this video live, go to the scifest2020.org. There's a question box right underneath Melinda's picture. You can send her questions during this live presentation. Sorry. Okay, I'll turn it over to you.
Okay, thank you. All right. So welcome. I'm so happy to be here. And let me see if I can make this. Oh, okay. All right. So I'm happy to have everyone here. Welcome to my home. The good thing about Zoom is I can invite you all in, and I am really happy to be a part of the Flagstaff Festival of Science, my favorite 10 days of the year. And I'm glad Todd said that about those STEM kits, those engineering kits. Those are really cool. You can learn how to make 3 different types of bridges. So please take advantage of that from Tinkertopia. And so I'm going to just jump right in, and we are going to learn how to make catapults today. So catapults are, I'm going to share my screen really quickly. And as I do that, I would like to mention that anything today that you create, please share it with me. I would love to see it. I am so interested to share science. That's one of the best parts, is to see what we can learn together. So you can email me at dofunscience@gmail.com, or just hashtag FFOS, which is Flagstaff Festival of Science, Catapult. And we will compile those images and videos. If you have videos, that would be great, and put those up on our social media. And I would love that. So please, participate in that way. All right, so let's get started. Get my mouse over there. Here we go. And down arrow. Oh, wow. Okay. First issue. Here we go. Oh, gosh. Oh, no. Okay. I'm exiting. Wow. All right, while it looks like my computer is thinking about something, so I'm going to stop the share and come back. All right, so PowerPoint's not essential. So what I want to share with you is that we're going to start by building a catapult. And a catapult is just something that hurls an object at a distance without using explosives. And so we are going to make our own catapult. And what you need to start with is just 6 popsicle sticks. 1, 2, 3, 4, 5, 6 popsicle sticks, 3 rubber bands, 1, 2, 3. So not too much, 1, 2, 3, and then one more item, some sort of a spoon. A plastic spoon would be what I'm going to start with, but whatever you have in your kitchen, and if you look around the house, you can modify later with other materials. So first thing we're going to do, take your spoon, put the spoon onto the popsicle stick. Take one of your rubber bands, rubber band that spoon to the popsicle stick, right? Just kind of there in the middle, get it secured. All right, and that looks sufficient for me. Now, I'm going to take my second popsicle stick, put it underneath the first one. Take the second rubber band and rubber band the ends together, the wooden ends together, not the spoon part. So there I'm just going to take the rubber band and put those together. And we are almost halfway done with the prototype. Okay. The next part, take your remaining 4 popsicle sticks, rubber band those together. This is going to be your platform. Now, if you have 3 rubber bands, that's awesome. That's great. That's all you need. If you have 4, you can even add another rubber band on there and scooch this one platform for the spoon. All right. So 4 popsicle sticks together, 2 here. Now we pry this apart, these 2 popsicle sticks, and place in between them the wedge that is our 4 popsicle sticks. And here we are done. That is it. You have your prototype that fast, right? So we can actually test this sucker. And so this is an object that will take a projectile. If we place the projectile in this spoon, the chamber here, put in the energy and release, then we will have projectile motion. So let's go ahead and just measure this and see if you have one that you just set up. We want to see how far it goes, get an idea of, is this actually working? So I'm going to pull my video back here, and I've got my test space all set up. So here we go. I have my prototype and projectile. So I also have a partner who's going to help me measure the distance and the height. This is Casey. And so here we go. I'm going to hold the end. So I'm going to hold this end of the projectile down with my finger. And then I'm going to place my projectile in, and 3, 2, 1, release. All right. Oh, it went off the charts. So I had a meter stick. It went up here and it's over 1 meter. Looks like about 110 centimeters. So I'm going to record that. So in science, we make a record, right? We have data. So I'm going to get a pen, 110 for the height. My version is my prototype. So I'm going to put prototype, and my range. Let's see how far my range is. That's basically the distance from the launch point to where it ends. So going back down here, another projectile, ready, and loading. 3, 2, 1. Woo! All right, where did that go? Looks like it went to 75 centimeters, or 0.75 meters. Write that down. So that's my baseline. That's where I'm starting from, right? 75 centimeters. Okay. Got my units there. Now you can use inches, that's fine. You just want to have some record of measuring how far it went. And even if you don't have a tape measure or a big ruler, you can just make put a little, I had over here, like this was my helper. This is my Stegosaurus helper, and he was helping me measure distance. So if you don't have a ruler, you can just put this as a place marker, and then that'll help you measure distance. Something just to put there, and then see if your next prototype is going to be further or shorter. Okay, so coming back. Now, so science is really hands-on, and it's something that you can do without any fancy equipment anywhere. All you need is a little bit of curiosity, and to understand a little bit of the physics also helps. So I'm going to go back to my initial slide and see if I can get this to work today. So I'm going to share my screen. I'm going to jump over here, share. Okay, so I will go to view, present. Okay, so here was our catapult, and that was what my model looked like. Those were our supplies. Catapult is an ancient device used for hurling objects, missiles. It was a military contraption, but it is basically just has stored energy that's released, and the object is flung into a trajectory that is projectile motion. So you can see here that it kind of looks like an umbrella. The projectile motion, you start off, in this case on the ground, and you have some upward velocity, which would be velocity Vy, and some forward velocity, which is Vx. And the upward velocity go up, it stops moving upwards, and it goes back down. So that's the Y component. And then the X component, absent of air resistance, is just going to be going straight at that same velocity. Now, if you just increase that velocity, increase that velocity, increase that velocity, you will actually send your projectile into orbit. And that's what a satellite does. You just get that sucker going fast enough and high enough in the right angle, and it will just, as it falls down, the Earth is actually curving. And so it will just keep falling towards the Earth and it will go into orbit. So pretty cool. All right, so let's go. We measured the height and the range, or the distance. That was what we had as our goals for what we could quantify and put a number on, right? We had a prototype. That's our working model. That's this one. So hopefully you have some sort of working model. If you don't yet, that's okay. And if you don't have popsicle sticks, well, maybe you have things like these, right? Hi, Mom. My mom's watching from Hawaii. We grew up using chopsticks when we would eat food, you know, and you might end up making some sort of catapult that looks more like this, right? With some pencils, something that's lying around. So anything that has the same basic shape you can use. All right, let's consider the physics. Conservation of energy. I'm going to ask you a question, and I'd like you to think about the answer before I tell you. Where did the energy come from that ended up hurling that object through the air? That energy of motion, where was that energy? Where did it originate? Where was it a couple hours ago? Where was that energy? It was somewhere. So when I thought about this, my best answer was that the energy was in the lunch that I ate. It was actually sugar. I ate a big sugary lunch, and then that sugar went into my muscles, and then my muscles stored it for a while. And then I took the energy and I took the projectile and I, pressed down. So my muscles were contracting. That goes into the energy, potential energy in my muscles, and then the kinetic energy, I'm moving, and now kinetic energy stored in the elastic deformation of the spoon, right? So I'm actually, these molecules are getting stressed and strained, and they are not happy in that orientation. And as soon as I let go, it's going back. So potential energy comes from that's going to launch the projectile is coming from the deformation or the stress in this material. And then we stress it, and then, doesn't fall off. Boom. Okay. All right. Now, okay. Wait, am I sharing my screen? I don't think so anymore. Okay. So now let me go forward. Okay. So kinetic energy. All right. So what are the things that are going to make the projectile go further? Higher initial velocity, right? So if you get that sucker launching faster to start with, it's going to go further. Okay, so higher initial velocity. And let me see. Okay. Share. Desktop 2. Okay. So what I wanted to share my screen here with you guys is to show you, this is a diagram from a free open source resource. I just want to let you know there's tons of really high quality material on the internet now. And OpenStax is a nonprofit organization. It's funded by grants, and it has textbooks of all varieties, and you can go in there and find college level information. And so if you just search OpenStax and you go to college physics, there's a college physics textbook and you can access it. And this is just one of the problems that was an example in that textbook. And it shows that, you know, if you have 30 meters, that red arc, it's going to be shorter than 40 meters per second initial velocity, which is the purple arc. And then the faster velocity, the 50 meters a second, goes all the way to the end. And so initial velocity, if we can maximize that, if we modify our prototype and try to maximize that velocity, maybe we could go further. And so one of the things that I was thinking about, well, how could I modify this, right? And I happen to have, you know, some different spoons. And so I was thinking, well, what about if I deformed this plastic, right? Is this stronger? Would it have a stronger recoil? Would I get a higher initial velocity? So I'm going to make another prototype with this spoon right here. Super easy to do. And while I'm doing that, I'm going to form a prediction. I'm going to form a testable prediction. And there's a huge word that we use in science that is used to represent a statement that is testable. And it starts with an H. So do you know what that word is? It starts with an H, and then a Y, and then a P. So the word is hypothesis. So you make a hypothesis and you say, I think because of the change in the material, that this model is actually going to have a distance that's further. I think that my range is going to increase, okay? And let's see, I should probably make a hypothesis about the height as well. So what do I think is going to happen to the height? Now, your hypothesis doesn't have to be the same as mine. It's not about being right. It's just about being curious and asking questions, right? And if I get it wrong, then that's actually a good thing. That means I'm learning something. It's not about knowing the answer ahead of time. No one knows the answer ahead of time. That's why we do experiments, right? So my hypothesis is that it's going to go further and higher. So we will see. So I have just made a second prototype. Here we go. And I'm going to test this now. All right, come on down. Here we go. All right, number 2, same location, right? Not changing anything but one variable at a time, one variable at a time. Same location, same type of projectile, same initial orientation. 3, 2, 1. Oh, what was the height? Oh my goodness gracious. Okay, gonna have to get out the meter stick. Here we go. 1 meter and then 139. Okay, so it went higher. 139. 139 centimeters. Okay, 139. And this was with the what is this? Half tablespoon spoon. Okay. Now distance. Okay, distance. Here we go. Distance. Ready? 3, 2, 1. All right, what is that distance? Okay, so the distance is 47. 47. Okay, how does that compare to what I had before? All right, 47. Okay, so with the green spoon, I went from 110 to 139. So it went higher. And I went from 75 to 47. So it actually did not go as far. So I got half of the hypothesis supported and half of the hypothesis, the other hypothesis was rejected. So it turns out that just between these two prototypes, if I wanted to build something that I wanted to go higher, then one of these is going to be more ideal, right? And which one was that? It was the green one, right? But if I want something that's going to go farther, then it would be this one. So it's really important to know, what are your goals? What are you trying to achieve? And then you can try to maximize that. All right, I'm going to come back. And what else do we have? How else could we modify this? All right, I'm going to go back, share my screen, share screen. Here we go to our desktop. Okay. All right. So initial velocity. Oops. Yeah, I have a trouble here again. Interesting. Okay, I'm just going to scroll through this way because I'm having issue. When you increase the velocity, you increase the range. And here, okay, so this is actually a series of trajectories for different initial velocity. So if you have an initial velocity of 2, it's this lower one here, which is dark blue. And if you raise it to 4, it gets further and goes higher. And if you raise it to 6, further and higher, and green, further and higher, right? So you are getting further and higher. What I want you to look at is the shape of this parabola, or this, what would be like a nice umbrella shape. Usually in the previous picture, it was symmetric. See how the left and the right side from the line that drops down from the top is the same? That's an ideal scenario. That is a textbook problem. The real world, guess what happens? What is happening here? We are not seeing what we predict. So I wonder, what are the forces that are acting to make that shape change? All right, so there's a force that's acting down. What's the force that's acting down? Do you have that in your head? All right, it's the same thing that's keeping me on the floor. Same thing that's pushing this object down. And what about that force that's pushing it back towards where it started? What would be that force? Can you think of that? Okay. Well, if you thought of drag, then you are on the right path, right? So air resistance would be stopping it from moving forward, right? And if we were to look, so in this room, it doesn't look like anything's around me, right? It's empty space, but actually it's filled with millions of molecules, right? What's the number one most common molecule in this room? My college students usually don't have the answer to this. What is the most common molecule flying around hitting me in the face? 80% of the atmosphere, nitrogen. Okay, so lots and lots of molecules, nitrogen, carbon dioxide, oxygen, right, slamming into me. And I usually don't feel it. It's not too big of an effect. But if you start throwing something through the air, it starts to be an issue, right? So if you were to zoom in and look at that ball, it's actually getting hit by all these atoms. And so that is air resistance or drag. Okay, so why do we care about that? Well, I'm thinking about another modification. The modification I'm thinking about is for the projectile. What kind of projectile would we use to get a higher range, or to get a higher height and a further range? So I'm going to stop my share and let's look at what I have. So here, oh, look what I have. Can you see that? Do fun science. All right, this is a ping pong ball, pretty light, right? So the mass is not very heavy. My initial projectile was this, right? So these are pretty close, right? And I don't have a scale. I should have brought a scale and then I could actually measure the heaviness. But I can still, even though I don't have a scale, I can still test it and see. What do I think is actually going to go further? Oh, this feels a little bit heavier, maybe. Okay, I'm gonna go with this one. Okay, I'm gonna go with the ping pong ball. I think it's gonna go higher. So my hypothesis is that the ping pong ball will go even higher than the this craft ball, and that it will go even further. Okay, so let's go test it. All right, and I'm just gonna pick my prototype here, my initial one with the plastic spoon, and this guy, and then we'll test it. Okay, here we go. Ready? Okay. Same initial conditions, only one variable at a time. This time the variable is the ping pong ball or the projectile. Ready? 3, 2, 1. Oh, how high was that? Okay, let's get this. Woo. And we go up to 16 116. Oops, gosh, can't see both of those, can you? 116 height. And this was with the ping pong. Ping pong. All right, and what's the distance? All right, one more time. One more time, down. Distance is, here we go, ping pong ball. 3, 2, 1. All right, what is that distance? The distance is, let me see. Okay, I got my finger there. You can move that 68 centimeters. All right, so I'm recording my data. It's always good to have a log as a scientist. 68 centimeters. Okay. Well, it was kind of intermediate. So my results, it turns out that it didn't go as high as with just the green spoon. And it didn't go as far as the original craft ball, right? So I'm getting some information there. So, oh, I wonder why. I wonder if I actually measured the surface area and measured the mass, if I could figure out why. And that's really what science is about too, being curious. Oh, that's an interesting result. I didn't expect that. I wonder why, right? And maybe I'll just test some more things to see if I can see a pattern, right? So instead, let's see, what else could I test? I could test, what about this? Oh, do you think this would go very far? Is this gonna go further than my ping pong ball? And if not, so why not, right? Okay, let me test it real fast. Here we go. And then we'll look at some examples from some other people. Okay, I'm gonna test this one. So the feathers, ready? 3, 2, 1. Oh, did you guys see that? It went about this far, just a few centimeters. 3, 2, 1. Oops, 3, 2, 1. Yeah, this thing, lots of surface area, right? Potentially lots. This is like the epitome of drag, right? So this thing has a lot of things it's hitting. So not that aerodynamic. Okay, all right. So let's go back. Doing great here. I want to show you, I want to share with you a few catapults that a couple friends of mine made. So we're going to go back. I'm going to share my screen and going over here, desktop 2, share. Okay. And so I'm just going to skip that for now. So here is a good friend of mine, Zach Youngling, right? And he's my colleague, Kurt Youngling, who teaches geology here at CCC, his son, and they participated in the Catapult Challenge. And look at how innovative they were. They have bungee cords here, so that's storing the energy, and they have a snow shovel. And they even sent me a video. I'm going to go right behind here. And let me just click on that video. You can see they live, Kurt's got a little bit of a commute to Flagstaff. Sedona. Wow. All right, sorry, getting a little excited. That was fun. And then we have another view here of the same, right, catapult that they made. 3, 2, 1, launch. Woo! Okay, right? Bigger projectile. That was scaled up prototype, right? I gave them the prototype and they're like, hey, elastic energy, this is elastic, and look what they found in their garage. So nothing is off limits. Okay, I want to just show you in slow motion, projectile motion here. This is Casey, and oops, oh wow, here we go. Enlarge it and show you in slow motion. So I did this on my iPhone. It's really actually easy to do. Great, I lost it. Oh no. Okay, well, shoot. So just imagine, use your imagination that projectile motion in slow motion. All right. C'est la vie. Okay. While I'm sharing the screen, I also want to show you this really awesome resource that you can actually use a computer simulation to test your different parameters, so like angle and velocity. So if you go to that site that I said for the college textbook, and you go to chapter 3.4, you can actually access this free web interactive projectile motion app, and you click on it, and oops, you go in and let me see. You will go in and you'll be able to manipulate the cannonball, and you can change the angle, and you can add air resistance, and it'll give you a target. So it's a really fun interactive game, and it's true physics. So really fun. So that's an opportunity for you to do that. And let's see, go forward. Okay. All right. So just think about, what could you modify? Here's just another idea about what to modify. What would happen if you change the angle of the spoon? So I'm gonna pull out here, stop the share. So what I'm talking about is this, right? This right here, okay? So here we started with this. What's gonna happen if you change this angle? And sometimes it really helps in physics to think of extreme examples. So what would happen if it was almost flat? How would that, maybe you can have an idea how that would change it, versus if it was almost vertical, right? How that might change your projectile, right? And then you can test those. And let's see. So I will let you do that on your own. So those are things that you can do, take pictures of, and please, please, please send me a picture of your projectile, or at least your catapult. That would be so much fun for me. I'll hang it on my wall. You can see I love to decorate with physics type information and graphs. And let's see, what else do I have back there? Okay, I think we covered almost everything. So let me just say, I'll ask Todd if there are any questions.
Awesome. Hey, that was great. And check it out.
Oh my gosh, let me see. Oh, wow.
So yeah, I was having the same issue. It was going really high, and I was trying to figure out how can I get it to go further. And so, but I wasn't, building with different materials like you were just showing us. So I can't wait to try it with something different. Now, you called it a prototype, and can you explain a little bit more to maybe to the kids? Why a prototype? Why is our first working model called a prototype?
Yeah, so you really want to start simply. You have to have somewhere to start, and the simpler you can have your basic beginning model, it really can show you what's at play, right? If I have lots of bells and whistles, and I decorated, and I have the stegosaurus on there, and I have him holding a pencil, and then it's hard to figure out what's actually going on. So you want to start a really simple, what appears to be really simple. And in fact, in physics, you find out pretty quickly that even the simplest scenario, there's a lot of stuff going on. So prototype is the first working model that you can make, and then you test it, and then you modify it, and then you look back and say, is that an improvement, or maybe we should go back and look at some other way to modify it.
Awesome.
Yeah.
So before I bedazzle this thing, I should probably go through the rounds of testing it to make sure it works, and that bedazzling it's not going to change the way it works. So that's great. Something else, when you were testing yours, you kept it on the floor, but you also said, from the same location, use the same thing. And, in science, I guess we call those controls. Why are those important for your tests?
Yeah, such a good question, right? It is so important, because if I change 10 different things at once, right? If I go back and now I'm pressing really, really hard, and I'm also, I've moved it. So I've moved it from where it was initially, and then I take my measurement I'm not going to know if it's because I pressed really hard or because I changed my spoon or because I moved it, right? So it's really important to just change one thing at a time. And that can be really hard to do because you think, oh, no, I know I'm going to change 50 things and it's going to work better. And then maybe it does work better, but you actually have no idea why. So, oh, I wanted to show you some other examples that I made too. So these are some things, I don't know if you can see them, but if this was just from, I was thinking, well, what if you don't even have a popsicle stick? You probably have some toilet paper in your home, right?
Yeah.
So this is actually, it's more of a lever arm, but you can have just a rubber band here and put a projectile in that. Actually goes pretty darn far. I had made one with highlighters, right? This one was actually a student that made this. It was really heavily engineered and it works very well. Again, oh, and here, this might be cheating a little. You've got to, and you have to be careful if you have something like this, but like some sort of clip, right?
Pretty clever.
Or this.
Yeah.
So yeah, it's fun just to go around your house and see, what you have.
Yeah, he brought it, the whole kitchen and the sink with all the tools. That's awesome. Kathy from Flagstaff has a question. Does it matter if your object is round, flat, or even liquid?
Oh, that's such a great question. Yeah, I wonder how would that affect the impact, right? So if something is going through the air, right, and it's a big surface like this, right, it's going to bounce into, say, maybe 100 different molecules. But if it's only this big, if you turn it on its side and say it's going through the air like this, maybe it's only going to hit 2. So that means it's actually going to have less resistance. It's going to fly through a lot faster. So that this is the aerodynamic design. It's really important to have a shape that basically has a small surface area that's impacting that front, right? This is going to go a lot. If I threw this like this, I think it wouldn't go as far as if I threw it like this, if I could throw it really well. And if it was liquid, that would be a challenge because it would probably break up as I'm trying to throw it. So yeah, the type of material, super important, and the shape of the material. All of those things, so interesting to think about. Yeah.
Yeah. I think Kathy's probably getting ready for a food fight, thinking about different objects around this time at dinner. No. I could think of a bunch of things at the dinner table. But something else too, your description of the air molecules and causing drag, it kind of reminds me, we've all done this, the kids watching and adults, even the older kids like me, you stick your hand out of the window when your car's moving, and what do you do to feel more pressure and what do you do to feel less pressure is kind of an example. You hold your hand like this, flat if you want to feel more wind, and then so your depiction is something I can relate to with that. So, and as kids are thinking about this, I'd be interested to hear your thoughts. How this applies even space science, and you said aerodynamic engineering. If you're going to land something on Venus compared to landing something on the moon, what are the factors we have to think about for things that are moving like that?
Oh, that is such a good question, right? What's the atmosphere like? So what's the atmosphere? Isn't Venus the thickest atmosphere of any planet in the entire solar system?
It's pretty dense. It's 92 times that of Earth. So,
wow, that's amazing. Yeah, that would be really hard. And you'd probably experience a lot of heat, right? If you're trying to push through that, it's basically friction. And so you might burn up on entry, right? Because when you think about why the heck is something burn up when it comes through the atmosphere? Is someone up there setting it on fire? No, it's because it's flying through and smashing into all those particles, and that's friction. And when you rub something super fast like this, that gets hot, and you do that enough, bursts into flames. So yeah, if we could send this projectile fast enough, we could probably, maybe, I don't know, maybe we could get it to burst into flames. Maybe someone could do that and send me a picture.
Yeah, that would be awesome. Well, Melinda, this has been great. Thank you so much for sharing this. And I'm excited to see all the pictures that, get sent in with that. What's that hashtag again?
Yeah, thank you. That hashtag is FFOS, which is an FFOS Catapult. So Flagstaff Festival of Science Catapult, one word.
So they could put that on their Instagram. You can find them later on Instagram, or they can email you. And what was the email address?
Thank you. The email address was dofunscience@gmail.com.
All right.
Isn't that the best? That's like my favorite email ever.
I'm kind of angry. I didn't come up with that email and have that as my email. That's awesome. So send your pictures to that email, which would probably be the easiest. And then you'll compile them, video or picture, and maybe we'll share them on our festival social media. So
yes.
So send them in. I guess what should we give everyone, about a week from this presentation?
How about 1 week, and then we will post them, and that will be really fun. And thank you so much, Todd. The Festival of Science is amazing, and I know you have great programming. Come on, right now, right after me, rabbits for dinner, and then through the weekend, and culminating with the hot spot in Yellowstone. So just what a great program that you have as every year.
Oh, it's a pleasure. I get to hang out with people like you. So
likewise.
And if you're for our viewers watching, please go to our website. You can fill out the survey where you can, if you liked an event or if you have some ideas to make the next festival even better, submit those ideas to the survey link on our website. That's scifest2020.org. And that helps us out so much. Again, everyone, thank you for watching. Melinda, thank you. Paul Morgan in the background, Kathy, our backup host. Thank you so much. We'll see everyone later.
All right. Thank you. Bye-bye.
Okay. Awesome. Melinda, that was so cool.
Are we off now?
We should be.
Oh, maybe.
Yeah.
Yeah, that was fun. Thank you. It was really fun. I'm so glad that you were there, and it's so nice to interact with someone, but I just pretended your smiling face was there the whole time. So
That was. Even
My
if you couldn't see it.
face was here too. It was great. Thank you.